Welcome to this explainer. Okay, let's jump right into it. Today, we're setting the stage for a deep dive into advanced Terraform troubleshooting. Specifically, we are focusing on surviving some of the absolute worst-case infrastructure as code scenarios out there. Because, let's be real, if you manage cloud resources, you already know things do not always go according to plan. So today, we're looking at the ultimate recovery methods. We'll cover how to pull your environment back from the brink when critical data just vanishes, and exactly how to execute surgical resource destruction without accidentally taking down your entire infrastructure with it.
I want you to picture this absolute nightmare scenario for a second. You log in, your cloud environment across Azure or AWS is just humming along, running flawlessly. But then, you realize your Terraform state file has suddenly, accidentally been deleted. The infrastructure itself is still sitting right there, but Terraform has completely lost its memory. Do you know how to stop a massive, catastrophic infrastructure duplication on your very next run? That is exactly the high-stakes puzzle we're going to solve today.
So why does Terraform completely freak out when this happens? Well, let's dive into this by fundamentally understanding how the tool actually thinks. Terraform operates on a declarative approach. You tell it the exact, steady state you want your infrastructure to be in, and it just makes it happen. It doesn't care about the individual steps to get there, it only cares about the final picture. This is vastly different from a procedural tool like Ansible, which is built to manage and configure infrastructure as it evolves step by step over time. Because Terraform is declarative, tracking that steady state is literally its entire lifeblood. If it loses that final picture, it panics.
And this brilliantly illustrates the strict boundaries Terraform operates within. While newer alternatives on the market, like Pulumi, offer this massive flexibility, letting developers write infrastructure using familiar languages like Python, TypeScript, or JavaScript, Terraform is a lot more rigid. It requires you to use HCL, the HashiCorp configuration language. It's highly human-readable and designed specifically to write infrastructure quickly, but you are strictly locked into it. Understanding this rigid declarative nature is absolutely key to grasping how Terraform tracks what it is built.
Which brings us to the actual brain of the whole operation, the terraform.tf state file. This file is the absolute source of truth. It's essentially a giant map that connects the current, real-world status of your cloud infrastructure directly back to the expected configuration files you just wrote in HCL. Without this specific file, Terraform has absolutely no idea what currently exists in your cloud provider, regardless of what your local code says.
Now, by default, this ultra-important state file just sits locally on your machine. But obviously, when you're working on a team, you need a remote backend so that everyone is sharing the exact same source of truth. You might use Azure Storage, AWS S3, or Terraform Cloud for this. But listen, there is a massive warning label we have to attach here. Because this file maps literally everything, it very often contains plain text passwords and API keys, which means encryption isn't just a nice-to-have, it's mandatory. The critical takeaway here is that wherever you store it remotely, that media absolutely must be encrypted at rest, no exceptions.
So, back to our disaster scenario. Imagine you did everything right. You securely place your state file in an Azure storage account, your team is collaborating perfectly, and then someone accidentally wipes that file out. The storage is suddenly totally empty. What actually happens if you try to run a Terraform plan or a Terraform apply right after this happens? Well, look at the sheer scale of the catastrophic fallout you're about to face. Because the state file is gone, Terraform assumes absolutely no infrastructure exists out there in the cloud. It thinks it's starting completely from scratch. So it's going to look at your configuration files and attempt to blindly recreate every single resource. Instantly, your infrastructure costs double, and worse yet, you are going to experience some incredibly nasty overlapping and cross-pollination between the original resources still running in the background and the new duplicate ones Terraform is forcing into existence. It is a complete mess. But hey, don't panic, because there is a lifeline. The fix for this absolute disaster is the Terraform import command. This is your ultimate state file recovery method. Instead of just letting Terraform duplicate everything, you step in and use Terraform import to manually map your existing real-world cloud resources back into a brand new state file. You're basically acting as a cloud surgeon here, teaching Terraform its memory back, one resource at a time until that state file matches reality again. It literally saves your environment from total chaos.
Okay, let's pivot from total amnesia to a completely different but equally high-stakes situation. Imagine a real-time scenario where you have 20 resources actively running perfectly in production, and suddenly you realize you need to destroy exactly one of them. Just one. How do you surgically remove a single resource without accidentally taking down the other 19 or completely disrupting the entire state file?
The answer is a brilliant, highly specific command, Terraform destroy -target, followed immediately by the resource type and the resource name. Instead of tearing down the entire environment and starting over, this command acts as a precision surgical strike. It lets you point Terraform directly at that one specific piece of infrastructure and eliminate it, leaving everything else untouched, perfectly safe, and humming along in the state file.
So, taking a step back, how do we actually prevent the messy code bases that lead to these accidental deletions in the first place? It's all about rigorous organization using modules. Every Terraform project starts with a root module, which is just your main working directory. From there, your root module can call upon a child module to pull in specific resources cleanly. And for wide-scale team sharing, you can utilize published modules loaded from public or private registries. Organizing your code into this kind of clean hierarchy keeps your infrastructure predictable and, far more importantly, safe. Now, if you've ever accidentally pushed staging data straight to production, and let's be honest, we've all been there, you know exactly why you need to choose between workspaces or reusable modules when scaling this organization. You really have two main architectural choices here. You can use Terraform workspaces, which natively allow you to manage completely separate state files for each environment, or you can rely on reusable modules, where you keep your core configuration in a single directory but pass different variables depending on the environment you're targeting. Both are incredibly powerful ways to isolate your environments and protect that precious state file.
But if you want a true bulletproof safety net hard-coded right into your resources, you need to use lifecycle meta-arguments. These are nested blocks you can add to virtually any resource. And the absolute standout here is prevent_destroy. If you apply this specific argument to a critical database, or say a storage account holding your state file, Terraform will outright refuse to destroy it. It's an incredible proactive defense against the exact types of accidental deletions we were just talking about.
And of course, before you even run a plan to create or destroy anything, you should always run Terraform validate. This command performs a really strict syntax check on your HCL files. It'll catch invalid syntax, missing trailing quotes, missing equal signs, or if you accidentally declared a module multiple times. However, just keep in mind, it does not check your aesthetic formatting. It only cares if the code is actually executable. So unfortunately, it won't settle the age-old debate of tabs versus spaces for your team. You're on your own for that one. Also, sometimes you just don't want to hard code values into your validated files, especially sensitive ones. If you need to provide a variable securely at runtime, it's a super quick two-step process. First, open your variables.tf file and completely remove any default value you have set there. Second, when you run your Terraform command in the CLI, you simply provide the new variable value explicitly during execution. Why do this? Because hard-coding API keys into your code files is quite literally a disaster waiting to happen. Injecting them securely at runtime keeps your code pristine and, honestly, keeps the security team happy.
Okay, as powerful as Terraform is, we do have to ground this explainer in reality for a minute by looking at its genuine drawbacks. There is no built-in error handling. You are strictly restricted to the HCL language, unlike the flexibility you get with tools like Pulumi. We just talked about Terraform import being a total lifesaver, but the truth is certain items are actually prohibited from being imported at all. It doesn't support script generation, there are acknowledged bugs in specific versions, and super frustratingly, backend configuration blocks cannot pull data directly from variable files. You actually have to construct them during initialization, which leaves us with a pretty massive question to ponder at the end here. With these real drawbacks, no built-in error handling, and those strict language limitations, will declarative tools like Terraform eventually be replaced by the flexibility of procedural languages? Or will the sheer power and reliability of the almighty state file always reign supreme in infrastructure management? It is a fascinating debate, and I highly encourage you to explore it further as you build out your own cloud environments. Thanks so much for joining me on this explainer, and keep building.